Okay, in this video I'm going to finish off my definite integral that I was calculating by using Riemann sums. So, when we left out in the last video, we had turned our definite integral into this equivalent form that we're now going to compute. And again, this is certainly the longer, harder way. If you know how to do antiderivatives, that ends up being the shortcut. But again, you know, this is kind of, to me, these problems just really show you where the stuff comes from. I think it gives you a better conceptual understanding. Okay, so in this problem, our index starts at I, is an I. Anything that has an I has to stay to the right of the summation. Well, this 2 over n, usually what I like to do in this case is I just pull it out front. And you don't have to do this at all. This is my own personal preference. Okay, when you have the summation of terms being added or subtracted, you can basically sort of think about distributing that summation. You can basically sum each piece individually. So I'm going to rewrite this as the summation from 1 to n of just 1, plus the summation from I equals 1 to n of 2i over n, plus the summation from I equals 1 to n of 4i squared over n squared. And then I'm going to do the same thing that I did with my n. I'm just going to pull everything except for i's out front. So I'm going to write this limit as n goes to infinity, 2 over n. The first part we'll just leave alone. Okay, in the second part, I think, though, I'm going to pull the 2 over n out front of the summation. So we still have I equals 1 to n. Notice the part that's being left over is the I, so I'm going to leave the I inside of there. And on the second summation, I'm going to pull the 4 over n squared out front. And then we still have the summation I equals 1 to n of I squared. Okay, so now I'm going to use these two formulas these three formulas about the summations that I had shown in the very first video. Okay, so let's see. Let's give myself a little more room here. Okay, so we still have the limit as n goes to infinity, 2 over n. Remember, if we sum up from 1 to n, we're summing the number 1 n times, so 1 plus 1 plus 1 plus 1 times, we'll have it n times, so we'll just get n times 1, or n. Then I have my 2 over n, but again, we said we can replace the summation from I equals 1 to n with the value n times n plus 1 over 2. Okay, so all of that, these are equivalent values, okay? So this is a shortcut for calculating the summation. Likewise, we saw that the formula for summing up from 1 to n of I squared, we said that was n times n plus 1. See if I can squeeze it all in here. Times 2n plus 1 all over 6. Okay? So at this point, now I've just got a limit problem that I have to simplify down. That's going to be a little tedious, but not the end of the world. Okay, so at this point, what I like to do is I distribute my 2 over n back inside. So if I take 2 over n times n, notice that the n's would simply cancel out, and I would be left with 2. If I multiply the 2 over n times 2 over n, well, that's going to give me 4 over n squared. And then we still have n times n plus 1 over 2. And then if I distribute it to the last piece, well, we'll have 8 over n cubed. And then we have n times n plus 1 times 2n plus 1 all over 6. And let's close off our brackets. Okay, so we're almost there. I am going to simplify this down just a little bit more. So the first part I'm not going to do anything with. 2 is 2. What I'm going to do in the next step is I'm just going to kind of rearrange things. Notice 4 over 2, well that would be 2. And then I would, in the numerator of my fraction, notice we would have n squared plus n, and I'm just going to put my n squared underneath the other n's. So I'm just rearranging the first part. Likewise, I would have 8 over 6, which would turn into 4/3. On the bottom, I'm going to put my n cubed. Notice on top, if I were to multiply, so here I'm going to be a little tricky. I'm not going to do everything. Notice if I were to multiply out the numerator, the highest powered term, I would get an n cubed, and notice I would get a 2n cubed, and then I would get some other stuff. Okay, so I would get n and 2n. That would be my 2n cubed. That's the only way you're going to get an n cubed term. And then you'd get a squared term, a term to the first power, and a constant. But I don't care about those when I'm calculating my limits, so I get lazy right there. Not lazy, just clever. I know I don't need them, so let's not waste our energies. So at this point, when you have limits at infinity, remember the trick is, okay, so the limit of a constant would just be the constant, so the limit as n goes to infinity of 2 is just 2. Remember, if you have limits at infinity and you have a rational function, if the degree of the numerator is equal to the degree of the denominator, the limit is just simply equal to the ratio of the coefficients. So these both have coefficient of 1 and 1. So the second part will turn into 2 times their ratio, which is just 1. Then we have 4/3 hanging out. We do the same thing. The limit as n goes to infinity. It's cubed and cubed, so we get 2 over 1 as their coefficients. So the limit as n goes to infinity of my last term will just be 2. And we've now finally calculated our integral. So notice 2 times 2 would be 4. We would get 8/3. When I multiply out 4/3 and 2. I can turn 4 into 12 over 3. So it says we should get 20 over 3 at the very end of it. So if you know the shortcuts on how to calculate these, I'll let you, again, this was the original integral. You can check and make sure, in fact, that that is the right value. But again, most problems you certainly don't want to do this way, but sometimes in a calculus class they make you do it this way. So, and again, I think it sheds a little more light on what's going on if you understand the summations and can think about the Riemann sum in terms of rectangles, and I think it just gives you a better conceptual understanding. So, alright, I hope these 2 videos help. If you have questions, feel free to post comments, and hopefully either me or somebody else can point you in the right direction. So, alright, good luck out there.